Hello and welcome to another Maths high-level video on option 9 calculus. So in this one I'm going to talk about Taylor series. And Taylor series are just kind of an expansion of MacLaurin series. And before we do that, let me just talk about the limitations of MacLaurin series, an important thing that you probably have not realized. So let me just explain this one to you. Now, we used it before to make approximations to the powers of v, right? We had our wonderful MacLaurin expansions here. So we could just say, okay, so what is e to the power of 2 truncated at the seventh term, right? At the k equals 6. Well, that's going to be, we calculated it to be 7.356, and we can subtract. You remember, we have actually the remainder for this Lagrange remainder, but I want it to be clear that if you still don't understand the Lagrange remainder that well, e squared minus this approximation, I'm 0.0335 away from the real value. It's kind of close, but maybe it's not that good. What if we had done this with e to the power of 1? What if I tried to calculate it with e to the power of 1? Well, realize what happens here. You see, before the numerator I had powers of 2. So these ones were not that small numbers. They're pretty kind of big, still like 64 divided by 720. That's, it's a small fraction, but it's still not like ridiculously small. Whereas here, I'm getting all the ones here on the top. So each subsequent element of the sequence keeps getting smaller and smaller, much faster than here. And if I add this up together, I get 2.71805 and so on. And actually, that's 0.000226 away from the real value. And you can see that this one works a lot better than this one. And the reason why is because these numbers are much smaller than these numbers here. Hence, each subsequent element of the series is much smaller. So the consequence of this is that the closer that the x gets to 0, here it's 2, here it's 1 in my MacLaurin series, the better an approximation this MacLaurin series become. I realize that. If I had 0.5 here, this would be even smaller than 1. If I had 0.01 here, these ones would be even smaller, like very small here. The closer I get to 0, the better these MacLaurin series approximation become. So, in fact, and this is important, in fact, if you look at the radius of convergence that you're given for some of these MacLaurin series, you'll see that sometimes I will only be able to use it if it's close to 0. If it's not close to 0 at all, I can't use it at all. My way around this is going to be Taylor series. And what I'm going to do with I'm just going to do a horizontal displacement of my MacLaurin series. Now remember, if I want to translate a function horizontally, I have to write x minus 1, x minus 2, x minus 3. Remember that, right? Think about the quadratics. I'm just going to do the same thing. If this is the MacLaurin series for a function, well, wherever I have an x, I'm going to write x minus a, x minus a, x minus a. And it's important also that every 0, it's not going to be the 0 anymore. Now I'm going to get f of a, f prime of a, f prime of a, etc. And these are the Taylor series. And actually, the remainder will be the same thing, just substituting with x minus a. And now c is not between 0 and x. Now c will be between a and x. And this is just a consequence of doing this horizontal displacement of my MacLaurin series. I just put it where I need it. I just put it where I need it so I can make a better approximation. These two here are the formulas in your formula booklet. Now, you don't get a formula for the MacLaurin series. All you have to remember is that you have to let a equal 0. And if a equals 0, you're going to get these formulas as you need them for your MacLaurin series. Keep that in mind. Let's use this Taylor series for a previous example. So as I get away from 0, my MacLaurin series are least reliable. And as I go away from a, my Taylor series will be less reliable. Now, here's my Taylor series formula. Let's try it for e squared. And let's see what the difference is now if I center my approximation around 1, around x equals 1, right? So let me build a series for 1, for a equals 1, sorry. Like, this is what they would look like. This is f of 1. This is f prime of 1. This is f prime prime of 1. This is f third derivative of e to the power of x 1, and so on. Just keep getting e's, right? And here you're just getting minus 1, minus 1, minus 1, minus 1, and then 2 powers, because it's a power series, power of 2, power of 3, power of 4, power of 5, etc. It's just filling in the formula. Now if I add this together, try getting at the sixth term, this is what I'm going to get. I'm going to get 7.38844 and so on. And this indeed is much closer than we were before because we just displaced it. So we're much closer to the actual value. This is important because we can now, before we would have to like make a lot more terms to get it right, but now we don't anymore. We don't have to make that many terms. We can just make, you know, as many terms as we need, but rather than having to make more and more terms, we can just center my MacLaurin series around the point that I need, put it somewhere closer, maybe even closer than 1 to 2, maybe something like 1.5. Or you can use natural logarithms to get something that actually doesn't have e's in here. Think about it. Now this seems like a bit of a stupid case, right? Because I'm using e anyway. I mean, how is this going to make my life easy? Because I have e's, and I could just calculate e squared. What's the point of this? I mean, how does this? And you need to have a bit of faith in Taylor series. They are very useful. You're going to see that in the next presentation. Let me give you, as a bit of a hint, a more useful example. Natural logarithm of x. Now, natural logarithm of x, I can't do the MacLaurin series there because it doesn't exist when x equals 0. But I can do it around x equals 1. So think about it. If I do it around x equals 1, this is what it's going to look like. You know, like I'm going to find the first 3 terms. So, you know, I write down the first 3 terms here of f of x. And I start doing, okay, so f of x equals the natural logarithm of x. Well, natural logarithm of 1 is equal to 0. Now, think about this for a second. If this is going to be equal to 0 and they ask me for the first 3 terms, well, 0 is not going to be a term in itself, so I'm going to need another term here because this one's going to go away. Now the first derivative is x to the power minus 1, and like f prime of 1 is going to give me 1. Second derivative is minus x to the power minus 2, and I'm going to get minus 1. Third derivative, I'm going to get 2, and so on. So when I substitute in my formula, this is what I get. And simply, this will be the first 3 terms of the Taylor series to approximate the natural logarithm of x around x equals 1. This complicated expression means this. Now they also asked me for how big the error is, or truncating. I'm going to use the Lagrange remainder here. So the next one is going to be the fourth derivative, right? And the fourth derivative around c, and 3 plus 1 factorial at the bottom, etc. Now the fourth derivative is going to be, this is the derivative of this thing here, so it's going to be minus 6 times x to the power of minus 4. So I just substitute it and put the c inside here. And the c is to the power of minus 4, so I can put it in the denominator, and I just put this thing at the top here. And I know that c is between 0.9 and 1.1. It says so in the definition. So in the question itself, excuse me. So I need to remember, I need the error to be as big as possible, because that's the way to be sure that I'm contemplating all the possibilities. So the way to make this bigger is to put something small here and something big here. And that's just what I do. And I get the error, which again, I put it negative. And, you know, it's just, I guess you could take the absolute value here. So that's it. That's how we use Taylor series. It's just the horizontal displacement of MacLaurin series. That's all it is. Thank you very much for watching. I'll see you next time. Goodbye.